So firstly, we will discuss what is this differentiation property with respect to time. For that, let us see first what are the conditions involved. So the conditions here are f of t should be continuous function. Its first kth derivatives, that means the first derivative, second derivative, third derivative up to nth derivative, they should be piecewise continuous functions defined on this interval minus closed interval minus L to L. Moreover, the integration of the absolute value of all the derivatives including the function should be a finite number. That means all these functions, the function itself, its first derivative, second derivative, third derivative up to n minus 1th derivative, they should be absolutely convergent. So this condition should be there. If this happens and if the kth derivative goes to 0 whenever t goes to 0, then we can say that the Fourier transform of the nth derivative of the function, that is defined by iota omega raised to power n multiplied by f of omega, where what is f of omega? This is the Fourier transform of the function, simple function. So if you know the Fourier transform of one simple function, so you can calculate the Fourier transform of its nth derivative using this formula. So this formula is very important whenever we have differential equations. So suppose let us see it for the first derivative case. For first derivative, let me calculate the Fourier transform of this first derivative f dash t. So the Fourier transform of this first derivative is equivalent to integration minus infinity to infinity f dash t e to the power minus iota omega t dt. So I'll call this as the first function, this as the first function, this as the second function. Why? Because we'll perform the integration of the second function. So first function as such, the integration of second would be the function itself, its limits from minus infinity to infinity, minus integration, the derivative of first one, so the derivative of this quantity, so it would be with respect to t. So these coefficients would come ahead, right? And the integration of this function is f of t dt. So now we can substitute the limits. The limits infinity, they are not substituted directly, so these are written like this. So limit b goes to infinity, the function's value at this point 1 by e to the power iota omega b f of b, and the function's value at the point minus b. So these are the limits, and this term becomes, what is this thing? The integration of this thing, that is nothing but the Fourier transform of the given function f of t. So this is according to the definition of Fourier transform. So now when you substitute this limit b tending to infinity, what does this become? E to the power infinity, that means 1 by infinity, and this is 0. So first term is 0, cancelled. And in the second term, when you substitute infinity here, it is equivalent to, it is not defined, right? So this term would come here. So this is 0. So we only have this term. So whenever we calculate the first derivative of the given function, so this is equivalent to iota omega raised to power 1 f of omega. And next we'll see what is this for second derivative. For second derivative, it would come out to be iota omega square f of omega. So what is iota square? That is equal to minus 1. So this comes out to be this quantity. So this result is very simple, but this is an important result which one should note. So this has an application to solve differential equations. So let us proceed and see how this is true. So now we are to look for the solution of this differential equation. Y dash is equal to 2y, which is equal to u naught t e to the power minus 2t, and t varies from minus infinity to infinity, where what is this u naught t? That is the unit step function. So now this equation is given to us. Firstly, we'll apply the Fourier transform, simplify it, and then we will apply the inverse Fourier transform to this particular function. So for that, what we are doing, applying this operator on both sides, the Fourier transform. Then because this is a linear operator, we can separate out the terms, take the constants out. from this from this operator Fourier transform. So now we have just studied what is the Fourier transform of y dash. It would be equivalent to iota omega raised to power 1 and the Fourier transform of y. Suppose the Fourier transform of this y of t is capital Y of omega, where omega is the frequency, t is the time. So it becomes y of omega here. So using this property, if the Fourier transform of y of t is capital Y of omega, then this becomes iota omega raised to power 1 capital Y omega, and this term is minus 2 as such. The Fourier transform of y is capital Y of omega. And what is the Fourier transform of this function? We know the Fourier transform of u naught e to the power minus alpha t, that is equal to 1 by alpha plus iota omega. So therefore we have this term over here. So now we can take y of omega common from both of these terms. So from here we have y of omega as this term. So this is the formula of a plus b and a minus b. So it becomes a square minus b square. So we have minus omega square minus 4. Or we can write y of omega as this quantity. Now in order to obtain y of t from here, what we do? We apply the Fourier inverse, f inverse, on both the sides. So for that we apply the inverse Fourier transform. So it would be Fourier inverse of capital Y of omega and Fourier inverse of minus 1 upon omega square plus 2 square. So this is the quantity. Now we can multiply by 4 here and divide by 4, right? So why we have done that? Because we know the Fourier transform of this function e to the power minus alpha modulus of t, this is equal to 2 alpha divided by alpha square plus omega square. So from here you can see what is the alpha here. Alpha is equal to 2. So alpha is 2. So we have this quantity, right? So what is the Fourier inverse of this? The Fourier inverse of this is e to the power minus 2 modulus of t. This is the answer. So and you can open this quantity whenever t is less than 0. Its value is minus 2 minus t. Whenever t is greater than 0, it's the value of modulus t, that is equal to t plus t only. So this is the final answer that we were seeking for the given differential equation, right? So from here we saw that whenever we have the Fourier transform of derivative of some function, that is equivalent to omega multiplied that number of times to the Fourier transform of the given function f of t. So I hope this is clear to you all.